Today's Daily Dose of Math has us doing some simplifications of exponents and radicals. Here we have 4 simplifications and they're all done with the same base, which is base 3. I'm going to solve these, but I'm going to put up some more that are in base 7 and in base 11. And I'm not going to explain every law of exponents as I go. I'm assuming the student has already been learning the laws of exponents, and I'm just going to show what the simplifications look like. This first one, we have 9, which is 3 squared, and we have 27, which is 3 cubed. We don't want to deal with 9 or 27. We want to deal with those numbers expressed as their simplest base and exponent. So I rewrite this. 9 is 3 squared, and I need a bracket so I can show the 8 exponent that's already there. 27 is 3 cubed, and I do the same thing. Now I'm going to apply the laws of exponents, and I have 3 squared to the 8, a power to a power. I multiply, so I have 3 to the 2 times 8, which is 16. And here we have 3 to the 3 times 2, which is 3 to the 6. Continuing down here, I have 5th root of 3 to the 16 divided by 3 to the 6. I subtract the exponents, so it's 3 to the 10. And now I have to convert from radical to exponential because I need to check whether some of these are equivalent at the end. And in order to compare them, I don't need a mixture of radicals and exponents. So to do that, I keep the same base. Its exponent becomes the numerator of the new exponent, and the root index is the denominator. I have 3 to the 10/5, which is 3 squared. I have my answer for this first expression. Second expression, we have 81, which is 3 to the power of 4. But I need an extra bracket. And we have 27, which is 3 cubed. And I need the extra bracket. We have to be really careful here because of all the 3's. It's easy to get mixed up. Now we have 3 to the 4 to the 3. Power to a power, I multiply, so I have 3 to the 12, which is still being brought to the power 4, over 3 to the 3 to the 3, which is 3 to the 9. Still to the power of 3. Now we have 3 to the 12 times 4, which is 48, over 3 to the 9 times 3, which is 27. I'm dividing, so I subtract the exponents, and I have 3 to the power of 21 as my answer for number 2. Number 3, we have a 27. 27 is 3 cubed, and it's still to the power of 9. 3 to the 3 to the power of 9 is 3 to the 27. I'm converting between radical and exponent, so same base. 27 is my numerator. The root index 3 is my denominator. I have 3 to the 27/3, which is 3 to the 9. I'm finished. Now we move on to this one. 81 is 3 to the 4, which is to the power of 4. 9 is 3 squared to the power of -5, and 27 is 3 cubed to the power of 5. 3 to the 4 to the 4 is 3 to the 16. 3 to the 2 to the -5 is 3 to the -10. 3 to the 3 to the 5 is 3 to the 15. I have 16 minus 10, which is 6 plus 15, which is 21. I have 3 to the 21. And it turns out that 3 to the 21 is equivalent to this other one that had 3 to the 21. I have finished all 4 examples that are to the base 3. I'm going to replace these with 4 more questions with a different base. And to do that, I'm going to take advantage of a new technology that involves the light switch. Okay, that works fine. So now we have 4 more expressions, and these ones are with base 7. So the first thing I'm doing here is I'm converting 49 into 7 squared. I'll use a bracket. Now, 7 squared to the 7 is 7 to the 2 times 7, that's 7 to the 14. Converting into exponential form, same base, 14 becomes my numerator, 7 becomes my denominator, which is 7 squared. I'm finished that one. Here we have 49 cubed, which is 7 squared cubed. Need another bracket. Still to the power of 4, and we have 7 cubed cubed. I can do this right away. 3 times 3 is 9. 7 squared cubed is 7 to the 6. Still needs to be brought to the power of 4. And 6 times 4 is 24. We have 7 to the 24 over 7 to the 9, which is 7 to the 15. I finished that one. Now we have a 49 that is 7 squared, which still has to be brought to the power of 8, and a 343, which is 7 cubed, has to be brought to the power of 2. 7 squared to the 8 is 7 to the 16. 7 to the 3 squared is 7 to the 6. I'm dividing, so I subtract exponents. I have 5th root of 7 to the 16 minus 6, which is 10. And converting into exponential form, same base. 10 is my numerator, 5 is my denominator. So I have 7 squared. Number 4, 49 is 7 squared. To the 4, 343 is 7 cubed, so negative 3. Times 7 cubed, I don't have to do anything with this yet. 7 squared to the 4 is 7 to the 8. 7 to the 3 to the negative 3 is 7 to the negative 9. 8 plus negative 9 is negative 1 plus 3 is 2. I have 7 squared. In this case, 3 of the expressions ended up being equivalent. And now I'm going to take advantage of that technology again to put 4 more examples to finish off this video. And I think this technology, it needs a name. Since it involves me having to point at the power switch, I'm going to call it PowerPoint. This will revolutionize teaching, this PowerPoint thing. Okay, this is a little hard to read, so I'm just going to put a little line there to divide them. Now we're working with base 11, and this is one of the issues that affect students. We tend to use prime numbers as bases, and we don't want to always use the same numbers that might be on the student's test that is coming up, so teachers end up reaching for some weird numbers sometimes. But the thing is, once you are a student who's doing a course like this, you have to practice, you have to do a lot of practice, and you get used to seeing the numbers. You get used to seeing 121 and realizing, oh, that's 11 squared. When I see this 121, I convert it into 11 squared. It's still to the power of 4. This one is already an 11. This one's also 11 squared, power of 3. 11 squared to the 4 is 11 to the 2 times 4, which is 8, times 11 to the negative 5. 11 to the 2 times 3 is 11 to the 6. We have 11 to the 8 minus 5, which is 3, plus 6, which is 9. I have 11 to the 9. I finished that one. Now, 121, again, that's 11 squared. But I need extra brackets there because it's cubed, and then to the power of 4. Here we have 11 squared, which is also cubed, and is then brought again to the power of 3. Very confusing with all the 3's. Now we have 11 to the 2 times 3, which is 11 to the 6. And we have 11 to the 2 times 3. We have 11 to the 6 again. 11 to the 6 times 4 is 11 to the 24. 11 to the 6 times 3 is 11 to the 18. Dividing 11 to the 24 minus 18 is 11 to the 6. Not equivalent. Not yet. Okay, now we have another 121. We have a cube root of 11 squared to the 9, which is cube root of 11 to the 18. Converting into exponential form, same base, 18 becomes my numerator, 3 becomes my denominator. 18 divided by 3 is 6, so I have 11 to the 6. And that is equivalent to this one. So we have found two that are equivalent. And now let's do number 4. We have 4th root of 11 to the 8, I will leave alone for now, divided by 121 is 11 squared, but it is being brought to the power of 2, which is 4th root of 11 to the 8 divided by 11 to the 2 times 2, which is 11 to the 4, which is 4th root of 11 to the 8 minus 4, which is 11 to the 4, which is same base. 4 becomes my numerator. This 4 becomes my denominator. I have 11 as my answer for this one. It's not equivalent to the others, so we have found our pair of equivalent ones this time. They're both 11 to the power of 6, and it's number 2 and number 3. This is how we apply laws of exponents and occasionally switch from radical into exponential mode in order to simplify expressions like this and to test whether two expressions are equivalent. That is today's Daily Dose of Math. Please like, subscribe, and share.